Hello and welcome to another Tippling Philosopher video with myself, Jonathan M.S. Pierce. I am joined by my good friend and co-author, Dr. Aaron Adair. Aaron, we are going to speak tonight about a book that we have co-authored, which looks something like this, uh, named Aliens and Religion, Where Two Worlds Collide.
Why do I get the feeling I've seen that book somewhere?
It's because
Oh,
it's
I know.
imprinted
I've seen it at all of my good, high quality booksellers, where you can get
yes.
yours now.
Or 10. And yeah, the subtitle is Assessing the Impact of Discovering Extraterrestrial Intelligence on Religion and Theology. So we're going to speak about our book and we're going to go through it in a number of videos. And tonight's session is going to be discussing the more scientific part of the book, mathematical part of the book as well. That's your wheelhouse. We're going to be talking about whether aliens exist out there, what are the chances of them existing. But to start with, I guess the raison d'etre for the book is kind of trying to answer the question: does the existence of intelligent alien life have any impact on the probability of omni-God existing? Omni-God being the all-loving, all-knowing, all-powerful God. And we concentrate on Christian theology because that's kind of what we know, but we do touch on other theologies in the book as well. And that is what we seek to answer that question. But before we look at the kind of theological aspects of that question and the existence of intelligent alien life, we need to talk about what is intelligent alien life and is it likely to exist out there. So we're going to start tonight with that kind of that part of the book. Aaron, do you want to just introduce people to what your expertise is regarding this and
Yeah,
you know where you come from?
yeah. So my background is in science and specifically in physics. I had earned my PhD in physics from the Ohio State University. And when I was in undergrad, I also earned degrees in astronomy and mathematics. And for one summer, I was an intern at the SETI Institute. So I literally spent one summer using their technology for scanning the skies and potentially picking out extraterrestrial signals. So I have some direct scientific searching for aliens. And I have to specify scientific because, well, there's all the other people who go out and every sort of bright light that goes by is a UFO, and that's an alien. And the method we had was fortunately more reproducible, ultimately, even though it so far hasn't produced clear signs of evidence of aliens, but we at least know what to look for and how to convince other people that we didn't just confuse Venus for a UFO like many other people have.
Indeed, yeah, and that's something we'll get onto. And so you are a scientist, data analyst as well. Is that correct?
Data scientist is my
Data scientist. Sorry.
yeah. Um, and main thing there, and this is also somewhat relevant to our work here because data scientists also tend to do a lot of machine learning stuff, the AI sort of stuff that's been in the news. So while I'm not producing anything as sophisticated as like ChatGTP, the basic architecture for those sorts of things, I've worked with that sort of stuff before. And so the nature of what intelligence is and how it can also exist in silicon form is also somewhat part and parcel answering the question of if aliens exist out there and they're intelligent, how would we recognize it?
Yeah, and actually, there is a question we'll look at, which is, you know, could intelligent alien life be non-biological? So
Mm.
there might be that question we'll delve into. I guess we'll start where we start in the book, and this is a book I'm really proud of. I think we've done a pretty good job of making this topic interesting, diverse, looking at things from many different angles. This contains science, maths, philosophy, theology, psychology, a load of different topics, and yeah, really excited to have written this with you. And we've got some good plaudits as well for the book, some great endorsements.
Yeah.
Richard Carrier, who I've had on the show before, said it's the definitive book on the subject. I mean, that's basically as good as it gets, really. That there's no better book to get on this subject than our book, so that's awesome. And also, Stephen Dick, who's a NASA historian, has endorsed it as well, and he's actually the kind of main guy in that area, or has been traditionally. So that's really cool. But anyway, that's enough kind of patting ourselves on the back. Anything you want to add to that?
Well, I just want to emphasize that Stephen Dick was the chief historian at NASA and coined the term astrotheology.
Which is what is astrotheology?
Oh, that's just the subject of our book, Aliens and Religion, Where Two Worlds Collide, now available on Amazon.
Yeah.
Sorry, I'm very good at this salesmanship now.
So we're going to look at the idea or the question, are we alone, right? But before we kind of answer that with any, not that you can answer that definitively, but any kind of probability, let's look at a few principles first. Do you want to explain the Copernican principle and why that's important to the book, or to this subject, and the different contexts we might revisit that in?
Yeah. So the great advantage of living in the 21st century is we've been able to see how this whole scientific method thing has been treating us and see, hey, it works pretty well. So what can we learn from science, and where can we go from those sorts of things? And in many ways, people will point to the revolutionary work of Nicholas Copernicus in launching that revolution. Whether that's anachronistic or not, he's usually seen so central there because he's the first relatively modern person to say, hey, let's not have the Earth as the center of the universe, but make the sun and have the Earth revolve around the sun, and have that explain the observations of the planets, the moon, the stars, based on that combination of motions of the Earth rotating on its axis and going around the sun. And, well, so far was pretty successful, and we now are using that moniker to say, instead of placing us centrally and everything about the Earth is special and wonderful, we now see that we are just one of numerous planets around one star, and our star isn't the center of the universe either. It's one of hundreds of billions of stars in one galaxy of hundreds of billions of galaxies in the observable universe, and for all we know, our universe may not even be the only one. This makes us realize, hey, we look around, we see that we are one of many rather than something unique, and or at least not so unique in that we see that we're completely different than anything else. The Copernican principle is to say, hey, unless you have a reason to think otherwise, you're probably something more like the normal, the average, or close to the average than you are the exceptional. And fortunately, I'm wearing the right t-shirt again for this today, where I'm wearing my normal distribution t-shirt.
Beautifully geeky. I love it.
I got to. And just so the joke everyone knows is that this 99.7 confidence thing, that is a way of saying when you're within 3 standard deviations of the median of some sort of distribution. And so if we say, hey, if the Earth is like the other planets, it's going to be in some sort of distribution, and unless there's some sort of unusual selection criteria, Earth is going to be somewhere in the middle of that distribution rather than on the far edges, for the simple reason most of the examples are close to the average, and the exceptional ones are rare, because that's what makes them exceptional.
Yeah,
We can then apply that principle for, well, the whole dang universe.
Yeah, so we are sitting plumb in the center of the bell curve in all probability, right? It'd be far less probable that we're going to be exceptional in any kind of way. Now, whilst that started in terms of the center of the universe type thing, which is itself an interesting argument that pertains to whether we're the apex of creation. So already we can invite conversations of theology here and say, hey, if the Bible says that we're the apex of creation, and actually we're just one planet out of gazillions of planets, and the universe doesn't revolve around us, but we are just on kind of, it doesn't make sense to say on the edge of the universe, but we are, somewhere in a galaxy, somewhere in a huge universe, right? That plays merry havoc with the idea that we are the apex, but as you were going to say, this can also be applied to lots of different situations, and we'll talk about this in a future video. But to give you a taster, we are likely, if there are huge numbers of intelligent alien life forms out there, then if you're talking about intelligence, we'll be somewhere in the middle of the bell curve. There'll be instances of intelligent life that's hugely more intelligent than us and hugely less. In terms of morality, hugely more moral than us. In terms of being in the image of God, if you think that's a thing, hugely more than us. And in terms of suffering out there, that you might think that the amount of suffering we have on this planet is huge, like genocide, Ebola, cancer, so on and so forth, well, actually, there's going to be instances of suffering out in the universe that far outstrip our levels. Okay, so that's a Copernican principle in general, but we will return to that in those particular contexts. Right now, we're going to move on to another thing that's going to be useful for us to ground our conversation. That's a Kardashev scale.
Mm.
Do you want to explain the Kardashev scale?
All right. So suppose you have yourself a nice civilization. I don't know. This one here on Earth might do. You might want to say, okay, we are claiming that us here in the 21st century are more advanced, more powerful than we were 100 years ago, 200 years ago, 1,000 years ago. And we can also imagine what our technology might look like in the future and our capabilities in the future. So if we're trying to imagine how far out this scale could go and what we could possibly see, especially if we want to invite our alien friends along the way, how are we going to compare ourselves to those other civilizations that might be way more advanced than us or at the same level as us? How would we identify them at the same level? And especially at great distances, considering we're not going to be able to, anytime soon grab one of their microchips and see what the average distance between transistors is as a way of measuring. That's one thing that we just can't do. And we also need something general, because who knows what the technology of the future will look like. Again, 200 years ago, who would have been thinking about electronics? In 1,000 years from now, who knows? We might find amazing applications of neutrinos that just seem impossible now. It's really hard to predict things, especially about the future. But one of the things that we can say, because it's really rock solid physics, is to be able to do things, you need energy. You need to be able to do work. And the more energy you have, the more work you can do, the more stuff that you can potentially do. You might be more efficient with less, but still, if you have 10 times as much energy, that is the capacity to do 10 times as much. So we could say, all right, we can use energy as a scale, and a logarithmic scale that was developed by a Soviet astronomer by the name of Kardashev came up with the scale that would say, okay, a class 1 civilization is a civilization that can harness all the energy of sunlight that lands on the surface of that planet, which is a lot of energy. If you then move up to Kardashev 2, this is a civilization that is able to harness not just the energy that lands on the surface of that planet, but all the energy of the star that planet orbits, which is not just a little bit more, or even 10 times more. It's not even a trillion more. It's more than a trillion times more energy. Type 3 is on a similar rising scale, where you have control of not only the energy of one star, but all the stars of a galaxy, which is hundreds of billions of stars. So you got crazy amounts of energy if you're at type 3. And where are we humans? We're somewhere on a value of not a full type 1 civilization. We can't still harness all the energy that lands on the surface of the Earth. We're only a 0.7. And 0.7 might sound close to a type 1, but because it's a logarithmic scale, it's a little bit distorting of your intuitions. To go from our current level to type 1, we would literally need to have access to 1,000 times more energy production than we currently have, which is absolutely insane. It tells you there's no way we're going to do this with fossil fuels, because I would say, hey, look at the coal-burning power plant. We don't need 1,000 more of those. We need 1,000 more of those for every single coal plant there is, which is an absurd amount of coal plants, and not to mention all the global warming effects that would obviously cause.
And I guess why this is important is because if you want to travel at speeds that would get you across the universe to be able to visit other life forms, then you would need to be able to harness energy. The theory would be like huge amounts of energy if you're going to travel near the speed of light, so you can get somewhere, reasonably quickly, or at least as quick as you could possibly go.
Yeah, at least quickly and without destroying the entire economy of your planet. Like, maybe we could somehow find some way of harnessing all the energy produced in the world and devote it just to propelling one spaceship to close to the speed of light. But I don't think the idea of using the entire GDP of the world just to push one spacecraft is going to be something people are willing to do for decades. People like to do things like eat.
So we get to, guess we get to this situation where if there are gazillions of instances of intelligent alien life, how would they get to visit each other if they are, then in the same solar system as each other, then okay. But if you are astronomically far away, then you would need to harness energy at levels that are arguably fairly unrealistic. But then we might not, have the imagination or certainly the knowledge at the moment to be able to think how that could happen. It
Mhm.
conceptually could happen, I guess, but what we might start moving towards is the idea that if the distances are too huge and you require too much energy to move those distances, that it could be that there are multiple instances of alien life, but they might never get to meet because, as I say, they are quarantined by distance. It's just too far to be able to go because harnessing that level of energy is too difficult. Or it may be that it might be possible, but then the question is, well, why haven't we come across alien life forms if that is the case? But then we'll come on to that, and that's the Fermi paradox, sort
Mhm.
of. But we'll come to that after we deal with the Drake equation,
Mhm.
if you will. So talk to us a little bit about the Drake equation, how it kind of developed, what it sets out to try and find out.
All right, so this is an equation of trying to give a quick estimator of how many civilizations might actively be communicating in the Milky Way galaxy right now. And there's no way to like do a survey by sending a rocket ship going around all the suns in the Milky Way and counting up how many of them are sending out radio signals. Uh, we don't have that technology. We're not going to have that for thousands, if not millions of years. So what can we do? What can we do to make at least a reasonable estimate? And what Drake had done was say, okay, here are the factors that it seems like it would depend on. So if we can figure out reasonable estimates for these underlying factors, we can put them together and say, what is a likely estimate for how many active communicative civilizations are out there right now. So in that equation that you have highlighted, n is the number of civilizations, and then it's equal to a whole bunch of factors that are all multiplied together. The first one, r, is the rate that stars are forming in the Milky Way, which is something we can actually confirm astronomically with our telescopes. After that is the fraction of those stars that have planets. Of those systems with planets, the number of planets that are Earth-like there. Then what is the fraction of those Earth-like planets that develop life? What fraction of those life-bearing planets develop intelligence? Then what fraction of those intelligent civilizations actually develop communication abilities that can go out into space, especially like radio waves? And then finally, L, the lifespan of such a kind of civilization.
And of course,
Multiply
there's
those
an
together.
awful, yeah, and of course, sorry, I interrupted, but there's a lot of unknowns there, but I'm sure you're going to explain that.
Yeah. So of the numbers in there, the first three we have reasonable good limits on. So like the rate of star formation, we have a lot of astronomical data to go from there, and we can say that basically like a handful of new stars are forming in the Milky Way at any given year. In the past, it used to be much higher, but current rate we're really confident about. The fraction of stars with planets, that's something that we've only been able to really confirm well in the last couple of decades. When Drake first wrote this equation up in the early 1960s, we had never discovered a single planet beyond our solar system. Now we know there are thousands. And those are just the ones that we've completely confirmed, but you do the surveying and you realize, okay, just about all planets, or sorry, just about all stars have planets. In fact, there are planets without stars, so there's plenty of planets to go around. Now, the fraction of those planets that is Earth-like is a little bit more contentious, but we do have survey data, especially from what was something called the Kepler Space Telescope. As the name suggests, it was a telescope in space named after Johannes Kepler, a famous astronomer, and it basically just pointed at one part of the sky, and it was looking at stars to see them ever so often just kind of blink in brightness, where there might be a planet that has its orbit in line with our viewing. So when the planet goes in front of the star, it temporarily blocks a little bit of that light. And if it does that periodically, then you can realize, oh, that's the period of a planet going around blocking the light of that star. And then we can figure out what the length of a year of that planet is. We can figure out
Wow.
how far away it is from the star, and even reasonably approximate how big it is. And if you know how big it is, you can also estimate the mass of that world and figure out if it's rocky versus a gas giant. There's a lot you can do with just blinking lights. Astronomers are extremely
Wow.
good at getting a lot of information out of a little data.
Yeah, that's incredible. And I suppose there are questions then about whether you need planets like Earth to get life. I mean, are there other ways you can do life? Can life exist on colder or hotter places? Does it need water, carbon based, and all
Yeah.
these kind of questions as well? Just a
Yeah.
quick synopsis of what you think there.
Yeah, yeah, and it's part of the current definition of a habitable world, um, is that it has to be able to have liquid water on its surface. And some might say that's too stringent because what about life that doesn't need water? Thing is, one, we don't know of any examples of life that don't use water. Of course, we're a bit limited there. But two, water is the second most abundant chemical in the entire universe. So life that doesn't use water is trying to live with like two hands or two tentacles tied behind its back. I guess obviously depends on the life form, but it's just a really weird limitation. And water is just so good for so many things. It's a great solvent. It's then very good then for doing chemical reactions in there because it's also going to not like tend to mess with some of your other chemistries that are involved there. It actually retains heat well. So if you've heated up the water, it'll retain that heat for a good amount of time and hold that energy in. It's just like water is like really good choice if you're going to make that your primary substance that life is based on. So the edict from NASA is to find life, follow the water.
So, what's our best guess? And I know that there have been an awful lot of different answers. Garbage in, garbage out.
Yeah.
There's a lot of these are ranges that you plug in here. We don't know definite numbers, but we know, well, it's not going to be anything. It's probably not going to be anything less than this, and likely, and probably not going to be anything more than that type thing. So we will be we'll be plugging ranges in, I presume.
Mm-hmm.
What do you think is a good, robust answer to the Drake equation?
7. All
Of
right.
course.
So as I've mentioned, so the first three factors are the most constrained. The last three have almost no data to go by. So the fraction of Earth-like planets that develop life, we don't have the survey data to tell that because how many other planets have we gone to that have actually have life on them? None that we have found so far. So it's hard to confirm anything. So depending on who you talk to, they might think that, well, the chemistry of Earth is all over the universe, so there's got to be all sorts of examples of life developing. And others who will look at the chemistry involved and think it requires too many coincidences, it's a super duper rare thing. So if you can get anything from that fraction being as near as 1 as possible to the smallest number that you can plug into your calculator possible. Now, the problem is, those are what we call opinions, not facts. And I want to put in as much data as possible into these numbers. So one of the things that we did in our book is that we put in statistical distributions for those values that take into account the fact that we don't know. There are actual ways of saying, okay, if you have like no background information about what this value should be, you just know it has these sorts of bounds, it'll take this sort of shape. And if we do that and we do random pulls from that for our simulations, then we can see what the final distribution looks like. That showed us that more likely than not, we have neighbors in the universe. 50-50 if we have neighbors in the Milky Way galaxy. And when I say neighbors, I mean currently alive right now, not even considering, a million years in the past if there were advanced civilizations that went extinct, for example.
Yeah, and of course the answer is also going to depend on what you think the size of the universe is. So if you adhere to the theory that the universe is infinite in size, then actually you're going to have infinite instances of intelligent alien life, given that if you believe at least that there's intelligent alien life at least somewhere in the universe. If it's infinite, then the extrapolation is you've got infinite instances of that. Is that something you'd agree with?
Yeah, yeah. If the universe is infinite, then life existing elsewhere is a guarantee. In fact, if it's infinite, there's another civilization out there right now having this exact same conversation, but you have the bigger beard.
Yeah. Well, yes. True. Possibly. So you did some data in this, and that's what's great about the book. In the appendix we have some facts and figures and numbers and maths. I mean, it's relegated to the appendix because no one really wants to read them, right? But you have done them. So there is some original kind of science, I guess, done in the book. Is that
Yeah,
fair to say?
yeah, especially because it was, inspired by other science papers that were out there and trying to improve on their attempts at doing some sort of statistical modeling. There was a group from Oxford that had published on what are called the archives. So it's a preprint service where they had their stuff published, looked at that, and things that looked like they were hard to defend, in my humble, correct opinion. And so by doing our newer distributions, I think they're much more grounded in both rigorous statistics and actual data, rather than what they had done, where they basically had opinions from across the scientific literature. But the thing is, opinions don't make science. Opinions might guide where money goes, but the facts actually say what is reality.
Good stuff. I'm just getting. I'm going to play it at a faster speed. I'm going to double the speed of it. Let's get this out there. And here we go. Share that. And this is to give, while we're talking, people can check out the kind of size of the universe. But again, if it's effectively infinite, then that is oh, now it's got stuck. Anyway, so that is a Drake equation. And now my intuition is that there is definitely alien life out there somewhere. Again, we are just quarantined by distance. That is the main issue. But there is more than likely a huge number of instances of intelligent alien life. So that's where I fit on that. Are you in agreement with that?
Oh yeah. Even if it's relatively rare per galaxy, the fact that we have hundreds of billions of galaxies in the observable universe means, oh yeah, there are lots of people out there right now, let alone in our past and in our future.
Yeah, and that's something we'll come back to in the theological section. So now we come on to the Fermi paradox. So the Fermi paradox is all about, well, if there is all this life out there, then why the heck haven't we seen it? So do you want to explain what's going on there?
Yeah, so the name itself comes from a physicist by the name of Enrico Fermi. He was having a lunch with a number of his other physics friends. What do physics people like to talk about? Well, all the sorts of nerdy things. And what was really big at the time in the 50s was all that talk about all that new flying saucer UFO stuff. And in that conversation about us being visited, because thinking, well, there's got to be life out there. The galaxy's got so many stars, so many planets. There has to be people there. But then, as Fermi blurted out, well, then where is everybody? Where is the actual evidence that we have neighbors? And especially if there are all these, not just civilizations, but if they've also been around for oodles of time, why haven't they come by yet? In fact, one of the things you can do and estimate is, even with mere rocket technology, we humans could colonize the galaxy in a matter of tens of millions of years. So if a civilization never developed beyond the Saturn V rocket, basically, the thing that took astronauts to the moon, and that kind of rocketry, and just did that for millions of years, they would have filled up the entire Milky Way. Which means, okay, if it's possible to, with even 20th century technology, to potentially fill the universe, or not the universe, but the Milky Way, then kind of weird that nobody's come by to say hello or goodbye if they have, space weapons, as the question might be. So how do we resolve this problem that we not only don't have visitors, but we don't even seem to have any evidence of any advanced technology among the stars? Why is that the case? So lots of attempts to try to explain this problem. Everything from, oh, the aliens are out there, but they are purposefully not talking to us and they're hiding from us, so that way we can independently develop. We're basically in some sort of nature preserve or a zoo that we are observed and allowed to develop and evolve without outside interference. This is literally called the zoo hypothesis, and it was first called that by a scientist in the 1970s. Biggest problem with that is, well, people go to zoos all the time, and at least some people are stupid enough to jump the fence. Doesn't matter if it's elephants or lions, somebody has the great idea, usually with some liquid courage, to go play in the zoo pen. Well, now if you're going to do that with all the stars in the galaxy, it's like, okay, the chances that there's at least one teenager out there that's going to hop the fence and hop into our zoo pen is unfortunately pretty high. You'd have to have absolutely perfect policing across the entire galaxy for millions of years, which sounds very hard to implement. So usually that's not a great one. At least in my opinion, which is correct, that the zoo hypothesis doesn't explain the Fermi paradox well. Other things is one thing we talk a bit is a bit of game theory, and it's called the dark forest hypothesis. The idea that basically every civilization has their own internal incentive to stay quiet, because if the idea that there's a more advanced civilization out there and they detect you, they have a risk of you staying around, because then they could also become more advanced and then become a future threat. Only way to protect yourself and be able to grow is make sure you have no competitors that could even have a chance of advancing and taking you out. So everyone is quiet, and if anyone makes a peep, the more advanced civilizations will completely wipe out those stupid talkers. So the reason the universe is quiet is because to be noisy is to be like a loud chirping bird surrounded by hawks. Which I think is a pretty good metaphor there. But on the other hand, as I mentioned with the Kardashev scale, to be totally hidden, you also have to hide all of your technological signatures. Anything someone could look for and say, ooh, that looks like an advanced civilization. And among the things that would mean is you never reach type 2 civilization, because that will leave a noticeable amount of waste heat. You would be noticeable across the universe, that sort of way. And so you can't hide that. I even tried a few different ways to see, okay, what if you did this to try to hide this, and realize the energy requirements are huge and good astronomers would still figure it out anyways. So basically, either the aliens are nerfing themselves, or this is just not actually how this works. And in our case as well, as humans, people might be thinking, well, we've been sending out signals already, so we've already kind of failed the dark force hypothesis. We're the ones who lit the biggest campfire of all by shouting with our radio signals.
Yeah, so some people say that actually SETI is a really bad idea, because, you know, if there are more powerful, intelligent, advanced alien life forms out there, and we are going, hello, are you out there? It's kind of like advertising ourselves, and they might go, right, well, it's in our best interest to take them out. And so, you know, we are inviting our own demise, effectively.
Yeah. And the reason I would say that's probably not going to be the case is, one, the aliens already would be able to tell that there's life and technology here, even if we weren't sending out any messages into deep space, because with technology that we currently have or will be having in the near future, we're going to be able to tell, oh, this planet shows that it's going through an industrialization period. Things like that, or just the waste heat from that world, you're going to be able to tell is like, oh, they must be reaching Kardashev 1 scale abilities. And this will just be from the light our planet itself gives off, and has been giving off before humans even were walking upright. Aliens, a million years in the past, could have been looking at the Earth and were able to tell, oh, this planet's atmosphere has the features that show that it has life on it. So our existence as a life-bearing world was given away before the first human ancestor started crying for its mother.
So, I mean, there are other theories as to why we haven't come across aliens. Like, one of them is that we are the first of the advanced civilizations. What would be your answer to that?
Yeah, so in some ways, that first kind of goes against the grain of the Copernican principle, because our thought is, well, we're average. To say that we're first would say we are the most exceptional, if we are saying, literally, we're number one. Now, you could also say, well, it's like you're running a race, and you never saw anyone pass you, and you run through the finish line. It's like, maybe you actually were the fastest, if you didn't see anyone ever pass you by. In our case, we have been observing, and we don't see anyone else out there, so it's not initially an absurd position to take. The model that this is based on, though, comes from an economist by the name of Robert Hansen, and he was developing an idea of what are called the great filters, that there are these stages that are in themselves like super improbable to get past, and they're kind of like these gates, and if you don't get past this in like one good swoop, that you're basically blocked at that level forever. So either it's that life never forms in the first place, or multicellular life never develops, or even that when you get an advanced civilization, it tends to wipe itself out quickly because it develops nuclear weapons and elects Vladimir Putin. Things like that. Don't worry. I will just mention your favorite buddy, Lukashenko, right?
Or him.
I know, different channel.
So you think that isn't a particularly viable theory then, or solution?
Yeah, well, like, first off, the existence of these great filters isn't actually scientifically demonstrated. And from my own look at things, it seems like all these things that might seem to be these impossible hurdles to jump or extremely rare hurdles to jump, it looks like not might be so. For example, in the book for a while, I talked about what to me would initially seem like, oh wow, that's amazing. The development of the eukaryotic cell, and in particular, the fact that our eukaryotic cells, the cells that make up all multicellular bodies, consist of a nucleus and a mitochondrion. And that mitochondrion, usually called the powerhouse of the cell, for those who remember their high school biology or middle school biology, it might even be said now. But basically, this thing, it allows the cell to like get a way more energy to like respirate, to produce way more ATP for energy uses inside the cell. And basically, it would have been really hard, if not impossible, to get multicellular intelligent creatures without that sort of energy control. And the current theory on how the eukaryotic cell developed was that you had earlier prokaryotic cell with no mitochondrion, and the mitochondria itself was its own separate cell living on its own, and a big ol' bacteria basically comes along, eats the mitochondrion, but doesn't digest it, and they take on a symbiotic relationship. And it sounds like that's like me going, eating a hamburger, and not just digesting it, but somehow getting bovine superpowers. That's what it kind of sounds like. It's just this stupendously improbable sort of thing. And the fact that it probably only happened once in all the history of life on Earth sounds like, okay, there are... and also put some numbers on it. The fact of the matter is, the vast majority of the time on Earth, life was single-celled prokaryotic cells. In other words, the vast majority of the life was just the simplest form of bacteria for billions of years. And it could have kept going on for the longest time until this one freak accident in one place in the ocean this one time. So that kind of seems to say, whoa, isn't this like a stupendously improbable thing if it literally took billions of years and trillions of trials per second across the entire ocean of the world? But I revised my thought there because this sort of symbiotic relationship of like cells absorbing each other actually is not uncommon in nature. There are lots of other examples of this kind of symbiosis. So it made me think, okay, if nature kind of does this on its own already, then maybe it's not so super improbable. It's just that it became viable this one time on Earth. And most likely the time this happened is also important. This is also after a time when the level of oxygen on Earth had increased. So all those early bacteria, especially the cyanobacteria, are doing an early form of photosynthesis, which has oxygen as a byproduct. So the earliest forms of life didn't use oxygen or barely used oxygen or even found oxygen to be poisonous. Anaerobic bacteria, that's true for as well, even today. But eventually, there's enough oxygen in the atmosphere to actually start being useful for doing a much more efficient form of energy burning, of respiration using oxygen. Basically, cells lighting fires inside themselves to get energy. And that's what those mitochondria were able to do. And they really only then had like that huge advantage once there was enough oxygen there. So it might only make sense that you wouldn't have had this event happening a billion years before the great level of oxidization because the advantage just wasn't there yet.
So how does all of this answer the solution to the Fermi paradox as being,
Okay.
or how does that solution not a solution?
Yeah. So like I said, ultimately the point is all the proposed great filters, none of them can actually be shown to be filters. So there's doubts to think that this is even a reasonable paradigm. At least it's nothing that we can demonstrate from current scientific information. And because these theories that would explain us being first depend on that mathematical setup for the whole thing to work, if you don't believe the mathematical formalism fits what's actually going on, it's just a big pile of mathematics with a foundation of sand.
Right, fair enough. So so what is and another solution is just that life is really, really, really rare. I mean, you kind of touched on that with what you were saying just then. I mean, that's basically going to what's going to be the result of our simulations as well. That even the best simulations that we showed here. Let me just flip open the page to look, and the greatest number that we actually see here in our
chart, and this is along a logarithmic scale, suggests that basically, at most in our galaxy right now, we might have a handful of currently breathing civilizations. And if there's only, like, say, one or two other civilizations, they are tens of thousands of light years away. And we don't have good grounds to think that they're millions of years old, at least not on current evidence, on current projections, based on one of the interesting factors I mentioned in the Fermi and the Drake equation is the lifespan of those kinds of civilizations. Well, how long do those civilizations last? 10 years? 10,000 years? 10 million years? How could we possibly know? So we performed something that's called the doomsday argument, which is another way of taking the Copernican principle, but making Copernicus very scared. Basically saying, okay, again, assume we are an average observer. Then if we are observing our civilization, we're more likely observing it in some sort of average state rather than at its very beginning or its very end. And you can also use that to try to estimate what's the lifespan of that with some probability distribution. And so we do that with how long we have been an advanced communicative civilization, and then use that as our projection for the other civilizations out there, because we don't have any other evidence to go by. And the doomsday argument would suggest that us as an advanced communicative civilization only has a lifespan on the order of a few hundred years, which means, you can make a lot of progress in that amount of time, but if it takes millions of years to colonize the galaxy and you're only around for less than 1,000, well, it ain't gonna happen, Chief.
Yeah. Okay. So, to conclude this, how would you conclude this kind of section in terms of why we haven't found alien life and how much alien life might be out there? And obviously, it's going to be linked to the size of the universe. But
yeah. And when I talk about how much life there is, I at least try to keep it local, quote unquote, local to the Milky Way galaxy, just because if there's going to be any fighting chance that we ever visit them or they visit us, we're probably going to have to be at least galactic neighbors. To be intergalactic is just even more stupendous in terms of distance. But most likely the best solution is that we do have life forms elsewhere in the universe and probably even in the Milky Way galaxy, but are so far away and without the desire to travel those stupendous distances using stupendous amounts of energy for trips that will take tens of thousands of years just to mutilate our cattle or whatever reason they might want to come here.
I mean, that's a really good point that needs to be kind of underscored, which is if intergalactic or intragalactic travel, and I don't know that's the right word, is so expensive to do, then actually, why would you want to travel anyway? If it's just to pique your interest, you're never going to be doing. I don't go. God, I wonder what's lying under the rock, in the Antarctic. And then decide I'm going to go there at the cost of virtually my life and 90 years of my. It might take me 90 years to walk there just to look under the rock and go, well, that's brilliant. Now I'm dead, right? So. The idea, it's a really poor analogy, but the idea is that life forms aren't going to be bothering to do that unless they're really, really desperate for something or really need something, or it's really, there's a great return on investment. But I can't think of any particular scenario where you have that return on investment. Like why any life form would find the need to do that, to go that far. Like if it's for any natural resources, they're going to be natural resources much closer. Than traveling, particularly between galaxies. I mean, what do you have to say to all of that kind of reasoning?
Yeah, especially between the galaxies, it's almost perfect vacuum. So the whole time, when early humans were crossing the oceans, they could at least fish. They could at least breathe the air. Between the galaxies, there is maybe one proton per cubic meter. It is so nothing that nothing is almost an exaggeration for how much there is, because it's just so non-existent. But yeah, and also actually the argument that you made that it has to be worthwhile, I use for a back of the envelope calculation for how much energy would a civilization need to actually make the distances using relativistic fast space shuttles. And basically make it the same sort of economics for it was worthwhile for the United States to launch a space shuttle. So I try to use that as a comparison to say, hey, we at least willing to make this sort of investment for this rocket ship, even though it didn't have any direct economic benefit. Using that as basically a launch point, realizing, okay, at a minimum, a civilization that can get here on a space shuttle going 87% the speed of light has to be at least 1 million times more powerful than us.
So it just ain't going to happen, really.
Exactly.
And if it does happen, well, yeah. So actually, this kind of leads on to cosmic scale. So before we get to what intelligent alien life might look like, talk just for a short period about just cosmic scale. If we're talking about traveling within a galaxy, what is that realistic?
All right. Well, let's say you want to go to the nearest star to our solar system, named Proxima Centauri. And Proxima, because it's in our proximity, it's nice and close. Real, just hop, skip, and a jump. All you have to do is go to the moon, make a left, and then go. Well, there's the problem. How long you have to go? If you took the fastest probe we have ever launched into deep space, the Voyager probes, and if they were going in the right direction towards that star, it would take on the order of 70 to 80,000 years to get there. So, and to put into perspective, human civilization, in terms of like cities and writing, and that sort of thing, is only about 6,000 years old. So you need to basically spend 10 times the existence of our civilization just to get to the nearest star in our neck of the woods. And our woods are pretty darn big because our galaxy is approximately
that's our nearest other sun. Just to break this down to lay people, the nearest sun that has planets around it that could have life existing on it. So the nearest possible place for life. Would you agree, or meaningful life?
Well, we don't know if it has life there or not, but we do know Proxima Centauri does have planets.
Yeah. So I'm not suggesting it does have life, but that would be the nearest possible place that life could exist. Planetary life could exist, and so therefore, like if the very next place had life, which we've already said is going to be incredibly unlikely, we would still have to be traveling for at our present technology for 70-odd thousand years.
Yeah.
And
Yeah, and then of course, if you wanted to do a jump across the entire Milky Way galaxy, well, the Milky Way galaxy is about 100,000 light years across, which is 25,000 times greater in the distance. So, hey, it took you only 80,000 years to get there. Well, now it's going to take you 80,000 times 25,000. It's like, okay, yeah, you can do the numbers and say, stay home.
Yeah. SK here says, why travel by ship, not by light? I don't know how what that means exactly. Is there any way you can interpret that?
So some of the things that we want to do in the near future is actually send probes to Proxima Centauri using light. So there is a project, it's called Project Starshot, and the idea of using numerous megawatt lasers projected onto these extremely light light sails to push them up to a significant fraction of the speed of light. I believe they're talking about having something that would be on the order of grams in mass, but using all these lasers pointing at it, being able to get up to 10 or 20% the speed of light. Now, again, that's a huge number of extremely powerful lasers and something that's only a few grams of mass. That's definitely not how you're going to send people there. Maybe in the future, when we develop even grander laser technology, we could send rockets there, but then there'll be one other problem. If you use light to actually shoot the rocket there, how do you slow it down?
Yeah, because one of these things that you talk about in the book is that one way you could destroy another planet, for example, is just throw like a tennis ball at like really high velocity at a planet, and that'll basically you throw that at the speed of light, and you're destroying the planet. Would that be correct?
Yeah, get any mass going fast enough, it'll have so much kinetic energy, it would be at atomic weapon level. So yeah, get a bunch of tennis balls or any like kilogram objects, get them up to 99% of the speed of light, and you got yourself a non-fission nuclear bomb.
Yeah. So trying to stop yourself going at the speed of light, is going to be interesting. But that good question, SK. So thanks for that. And you could replicate from information. Is that something that's plausible?
So this sounds like something called a von
It's
Neumann machine.
right.
So this is basically a probe that can reassemble itself or make copies of itself. So you could imagine send
This
some
is
sort of device.
Star Trek. This is Beam Me Up, Scotty. Right.
No, this is pre-Star Trek because it's called von Neumann because it's named after John von Neumann, a mathematician and physicist.
Sure. I was going to say, but the principle is that not the principle of the Beam Me Up, Scotty? Like and hence you get the whole philosophical argument.
You're talking
like,
something else as well with teleportation. I see.
Yes.
Okay, there's multiple ways to interpret this. So I'll finish with the von Neumann, and then I'll talk about Star Trek tech. Okay, but the von Neumann machine is you're sending probes. The probes will still go at normal speeds throughout the galaxy, but it reaches a rock like a planet, and then it starts mining material to build more copies of itself, and then it can make millions of those copies and then shoot those off and basically fill the entire galaxy up, pretty much like E. coli splitting and filling up an entire petri dish, something kind of like that, but all electromechanically. With the beam me up sort of thing. So, as best we can tell, the technology of the teleporter is going to be impossible for a few reasons. One is that if I wanted to send Jonathan M.M.S. Pierce and accurately reproduce him on Mars,
Who
atom by
wouldn't wanna do
atom,
that? Awesome idea.
we need more Pierces. So if we want to make a perfect copy of Mr. Pierce on Mars, we would have to scan your body down to the level of the atom and maybe even to the subatomic level, because the bonding between the molecules and things like that will also matter. So we need to scan you really well. But to do that, we have to use light. And if you want to scan something down to the size of an atom or smaller, you need wavelengths of light smaller than that, which are also called X-rays and gamma rays. So what we first have to do is basically irradiate you and turn you into a plasma. So, first problem. The scanning process is lethal. The amount of data is obviously...
I'm beginning to think it's not a great idea, so let's not do this.
Yeah. Technically, the transporter is actually a suicide machine, but that's another philosophical discussion, maybe for later in the interview.
Well, if I get recreated though, it's zero sum. So no problem. I mean, this is a whole philosophical issue with the the transporter machine. Is, are you the same person if you're getting recreated and blah blah blah?
Yeah, it's very Theseus-ship-like in that, but the best way to show how much it is a suicide machine, and there's examples of this in Star Trek, where the transporter makes a mistake and doesn't actually send the person, but makes a copy of them, and so both people are in the transporter room. If that happened, and then the transporter's person said, "Oh, sorry, mistake, I'm going to incinerate you now," then you'd realize, oh wow, this really is a suicide machine. Yeah. I'm just copied elsewhere. But that's one thing, but also we also can't get the level of scanning needed because of something called the Heisenberg uncertainty principle, that you can't know the exact position and momentum of a molecule or a particle with infinite precision. So to actually recreate you completely would be actually impossible, that we can't actually get down to that level of precision to do what's needed. And of course also, to do the assembly at some other place that doesn't already have like an assembly plant, you would already have to have sent basically some sort of transporter pad there, which means you've already had to make the trip the long way anyways.
Yeah, good point. And this, I know this is going to excite you. So Kathy Rist has come up with Dyson Sphere. Can you explain that to the audience and why it could be, important or significant?
All right. So this was an idea developed by the physicist Freeman Dyson. And the idea is somewhat straightforward. Okay, what's the biggest source of energy in the solar system? The sun. What fraction of the energy of the sun actually reaches Earth? Pretty darn small fraction. So what if you could build a structure that captured all that energy and basically just like, not just solar panels just covering the Earth, but covering all the way around the sun in basically a giant spherical shell? That's the idea of the Dyson sphere. Collect all the output energy of the sun, and you have a Type 2 Kardashev civilization. And this is not just a little bit more energy than we currently have. This is on the order of trillion times more energy than we currently have. Now, the original design from Dyson would not actually be stable. So instead of it actually being like a solid shell, it would probably more likely be a whole bunch of orbiting platforms that would collectively be a swarm that blocks out all the light from the sun. And so the Dyson swarm is the more feasible version of what this future technology could be.
And of course, one of the interesting things to think about here is that you could detect that arguably from a distance as well. So if someone has developed this technology, it is something that we could in principle detect.
Yes. Yeah, it's something they won't be able to hide because one of the fundamental laws of physics is the law of increased entropy, the second law of thermodynamics. Basically, any machine has a tailpipe and it has waste heat. We would be able to detect that waste heat. And it's actually one of the things that astronomers have done with telescope time. Look for any odd infrared signatures that could be the sign of a Dyson swarm. So far, they've come up negative, but that would be one way of also detecting advanced civilizations that have literally taken all the energy of their sun and now can do who knows what with it.
So, let's get on to talking intelligent alien life. What does intelligence look like? What is intelligence?
Well, that's an easy question, right? No philosophical quandaries.
Yeah, but actually, so this is a notoriously difficult subject. Lots of people struggle with adequately defining intelligence. There are lots of different theories, maybe multiple intelligences, maybe so on and so forth.
Yeah.
How would you answer this question in terms of this book and alien life?
Yeah. So clearly it's going to be difficult to give the aliens an IQ test. And also the question, what does IQ actually measure? The joke is intelligence is what the IQ test measures. And what does the IQ test measure? Well, whatever that comes out, we call that intelligence. It becomes one of those circular definition issues there. But the method that we try approaching here is a more functional definition of intelligence that's used especially in artificial intelligence research, where we can refer to something as an agent if it basically is doing something that is performing some task for a goal, and it takes in inputs and adjusts the way it acts to better achieve those terminal goals. So an idea of an extremely simple agent would be a thermostat. Thermostat is able to detect something about its environment, the air temperature, and if it's outside of a certain range, turn the air conditioner on or off. So it's an extremely simple agent with the simple goal of bringing down the temperature to a comfortable range, what humans define as comfortable. But it's also not terribly in terms of intelligent, because what if the person who installed it got the wires backwards, and so when the temperature goes up too high, it doesn't turn the air conditioner on, it turns on the heater, and then the apartment gets warmer and warmer. Then the thermostat looks at this like, oh wow, it's getting warm, I really better keep that air conditioner on, and not realizing it's actually just blurring the heater. It doesn't learn and adjust its behavior. It's just a simple on-off switch. So what is intelligence? In that case, it's to observe its environment and change its outputs to better achieve its terminal goal. And the way that this might actually help us detect alien life is that, okay, a civilization out there that has terminal goals of, living and thriving and growing, they're going to be developing technology. They're going to need energy to do that, like the whole Kardashev scale argument from earlier. And that is going to then mean, all right, they're going to need more energy, and they're going to have all these other things that intelligent civilizations need. For example, they need to communicate with each other to actually do trade and things of the like. And what is the most efficient way to communicate at the fastest speed possible over the greatest distances? First thing that pops to mind is radio, because that can literally travel between the galaxies. Very quietly after a long enough distance, but light goes across the entire universe, and it does it at the fastest possible speed, and it's relatively easy to make. When I say relatively easy, we've been making radio waves since the late 19th, early 20th century.
So how far have our radio waves gone?
So, specifically ones that had enough energy to actually, get out of Earth's atmosphere and go out into deep space. That's usually said to be in the 1930s, more or less. So, in particular, the transmissions that were put out by Germany during the not the first Olympics, the Olympics in 1936. That's usually considered one of the examples of like really high energy transmissions that could actually go out into deep space, which was played on in the movie Contact, where the first signals that aliens saw was a transmission of Adolf Hitler, unfortunately.
Right. Okay. Right.
Yeah. Um, and of course, they would have been seeing images of Hitler before knowing anything about what was going to happen in the rest of the world. But nonetheless, that would mean that very, 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 very roughly, radio signals from Earth have been leaking out for about a century. Now, that means that that light has been able to travel 100 light years, which is also well beyond Proxima Centauri. Hundreds, if not thousands, of stars are in that range. But also, as that sphere of light signal expands, the signal itself gets weaker and weaker and weaker. It follows what's called the inverse square rule. So every time the distance doubles, the intensity goes down by a factor of 4. If it's 10 times further out, it's 100 times weaker, etc. Gravity follows the same sort of thing. So eventually, you get far enough away, and those radio signals aren't any louder than just the background noise of the rest of space. So it's probably not the case that those stars, even 100,000 years from now, are going to be able to pick up our signals and detect those transmissions from Germany. They're going to just be noticing not even anything beyond static, honestly.
So let's go back to what intelligent alien life looked like and move away from intelligence, because I think we get an intuitive idea of like rational, goal-oriented entities that are going to be using energy, right? What might they look like? We'll talk a little bit about biological versus electronic, like existence. I was going to say life, but existence.
Yeah. Of course, the question of what is life and can you have a non-carbon form of life, a non-respiratory sort of life, is an open question, which unfortunately we do not solve, but we know what the right answer is, but we'll do that in another stream. So, as mentioned before, like when we're looking for habitable worlds, we're saying follow the water. We're basically going to be looking for life of a similar kind of architecture as life is here on Earth. So basically, the two main elements or chemicals that matter is water and carbon. And mostly because water is abundant and has so many wonderful utilities for doing all the interesting chemistry, and carbon because it's able to produce long chain molecules and has so many useful functions in biological sorts of things. So carbon is needed for like the backbones of the sugar molecule. It's needed for DNA, RNA, etc. That basically all biology really comes down to what is it doing with the carbon atoms it has. So most likely, biological life, if it exists, it's probably using carbon. If anyone is thinking, well, what about silicon? Silicon has some things that make it kind of like carbon in that it has a similar outer shell for its electrons, so it can do similar kinds of bonding as carbon, but only similar, not identical, and the difference can become quite severe. And the easiest way to do that is there's actually way more silicon on the surface of the Earth than carbon. The problem is the vast, vast, vast majority of that silicon is in the form of rocks. And it's really hard to basically have that break out and do any interesting chemistry because it's just in a really stable state. There's a reason we're not rock people. It's really hard for silicon to break down and do the sorts of things of, I think was mentioned in that whole carbon cycle. So we see that sort of observations, and there's chemical reasons why silicon is probably not going to be out there. I'd love to be wrong, but it's at least initially improbable. So if there's biological life, it's most likely carbon-based. But if we're talking about advanced civilizations, well, we're now getting to the point that we're developing artificial intelligences. People are talking about, having cybernetics, or even just putting our brains and just uploading them to computers, because that will be a kind of immortality. Maybe not literally live forever, but at the very least, hardware that is much easier to continuously update rather than this flesh, which every year keeps showing me that it's not going to last forever. And updating this is much harder to do. Like going and getting a new RAM chip for my computer, that's no big deal. Getting new RAM for this thing, I go to the store and everyone looks at me funny.
Yeah, yeah. It's Homo Deus, which is Harari's book, talking about, I think, or no, it might have been 21 Lessons. One of his books, anyway, talks about how like this is seems to be one of the intentions for humanity is to extend our lives, to be able to, we're doing all these things to make our lives longer and longer. And of course, it's a hop, skip, and a jump away from Terminator. And when I look at to go to talk about another channel that I have, which is talking about the Ukraine war. There's this evolution of the war to looking at autonomous technologies and doing war through autonomous means, where you have maybe drones doing things on their own back, and then you start thinking, goodness me, we are actually moving towards a Terminator. Science fiction becomes fact, reality. But what are the chances of coming across alien life forms that are electronic rather than biological?
Yeah, well, there are, I think, two questions that we can answer there. That will we first see aliens in the form of their technology, or the aliens are themselves their advanced technology versus their biological form? So, for example, I could imagine an alien probe coming to Earth, but would that probe necessarily be alive versus just a robot that's able to do some basic surveying tasks versus an actual, like, fully autonomous, intelligent, but digital creature? And again, assuming that you can have life or intelligence or consciousness in silico versus in carbon form. I don't see why that's not possible, but again, with that caveat there. And it's just going to be so much easier to send something non-biological across the universe because, well, again, I don't know if you've been noticing, but I've been having a few drinks along the way because our bodies need constant replenishing of fluids, of food, of oxygen. Something that might require just a battery could just go into low power mode and just stay in that state for a very, very long time. For us, biological entities, we don't currently have the technology to properly deep freeze ourselves and unthaw ourselves in a way that doesn't require us to have to be rebuilt. For those who are wondering, well, why not? Yeah, just freeze yourselves. Well, one of the other disadvantages of water is that water is one of those few molecules that when it freezes, it expands, which means a cell that freezes expands and bursts. Now imagine that's bursting your neurons. Oh goodness. Congratulations, you've turned your brain into complete mush. So the first thing we'd have to do is somehow knit together all of your cells back together if we were to unfreeze you. So at the moment, cryogenics is not a good solution. And again, way more expensive than just sending a computer and just keep it in low power mode and just have it turn back on when it gets to its destination. It's so much easier to do that, and so why not do that? And also, of course, humans get bored. We don't like being stuck in tubes for years and years and years. So the idea that we'd be sending ourselves out biologically before we're sending out probes seems exceedingly unlikely. And again, look at the example of our space travel. Before humans went to the moon, dozens of probes went to the moon. Humans haven't gone to Mars yet, but lots of probes have. And also, of course, the other advantage is if a probe goes and it fails, okay, we lost money. Humans go and it fails, we lost life, and it was terrible, and we shut down the program.
Yeah, it's a really good point. And to maybe what we can learn from our own past might give us some indication that actually the first alien life form we might come across. I mean, first of all, it's probably going to be techno signatures rather than an actual substantive thing.
Yeah.
But if we do come across a thing, then it's more likely to be a non-life form.
Yeah.
Yeah.
Yeah, that's how I at least would order it. That most likely we'd first come across, they're probes. Next up, the aliens, but they're electronic, and then finally aliens, and they are biological.
And we've talked about the kind of signatures. So you might see waste heat in terms of the Dyson sphere or something from afar. You might be able to detect atmospheric pollution on a planet in another solar system somewhere far away, and that could give you an indication that actually, if there's pollution there, you can see the effects of different gases and whatnot in your evaluations of any given planet. You might say, okay, that's an indication of life. But what are the chances that life has already found us if it is out there?
So, suppose that the aliens are approximately the same level of technology as us right now. We are on the cusp of being able to measure the atmospheres of these planets in these other solar systems, these Earth-like planets in around other stars. Like the James Webb Telescope can't quite do that, but it's close in a few cases. So you can imagine our technology is close. In 100 years, oh my goodness, we're going to have that kind of ability. And that's just, us puny humans. If the aliens are out there and they're, say, 1,000 years more advanced than us, then they have wickedly better technology. And just to give you an example of one kind of technology that's theoretically doable, but maybe is 50 to 100 years away, using the sun as a telescope, as a gravity telescope, in fact. Have you ever heard of gravitational lensing?
No, you are speaking Greek to me.
Okay. Well, if this sounds like Greek to you, then I'm obviously speaking much better than I expected. I went to see the most recent Indiana Jones film, and they actually have people speaking ancient Greek, and it sounded better than the Germans speaking German.
Nice, good. Is that worth going to see?
I liked it more than Kingdom Skull, though the chase scenes, I was feeling a little bit tired after a while.
Okay,
I would say it's okay.
Okay.
And also the main MacGuffin, the Dial of Destiny, it's actually the Antikythera mechanism with Archimedes. So
which you've written on before. I in fact, when I heard that was in the film, I was like, Aaron, yeah. Anyway, so
yeah, okay, yeah.
Stay on target.
Okay,
Pierce,
yes.
Stay on target.
Yeah. So with the sun, any object that has mass, according to general relativity, warps the fabric of space and time, which basically means straight paths actually get bent. And this in particular with light. If you're bending light, though, that's exactly what a lens does. It bends the path that lights take and allows it to focus. I mean, that's how like the lenses in your glasses fundamentally work. But the sun is a big, massive object, so it's going to bend space-time and light around it. We actually were able to detect that already back in the late 19-teens, early 1920s to prove Einstein was right about that whole space-time thing. That was like the first, experimental confirmations of relativity. But now take that to the next idea. Okay, the sun is bending light. If it's bending light, it will also be focusing it at some point. And you realize, wait, if it's going to be acting like a telescope, and you do the basic math for like what resolution you get with the telescope, and it's based on how big its aperture is, how big its hole is with that lens, well, now you got an aperture the size of the sun. Imagine the resolution on that, and that's exactly what you're thinking. And it would estimate that if we had a solar gravity telescope, we would be able to look and see continental features on planets 100 light years away.
Wow, that'd be pretty cool. So when's that going to happen?
So, people are talking like having the technology in place in like 50 to 100 years. And
Really?
One of the biggest challenges is that focal point is beyond the orbit of Pluto. So it is not a hot skip and a jump. You have to send probes out really far, and you probably need more than one probe for the simple fact that your probe will be here, and so that would also then be indicating the direction it's pointing.
When you're holding a magnifying glass, right, you need to get at the right distance from the lens to be able to make any sense of what you're seeing. So that is, you need to be at Pluto before you can use the sun as a lens.
Basically, yeah.
Wow.
Yeah.
But
and of course, as you can imagine,
doesn't the sun get in the way?
So
like,
you
I can
also
see
need
through
to
a lens. I can see through a lens. Well, I can't see through the sun.
You're going to basically also have to put your thumb up and like block the light from the sun.
Right.
And that's something we can do. That's something like solar observatories have been able to do. But yeah, you have to block out all that bright light from the sun itself. But otherwise, then you get all the other light focused around the sun, and it's then concentrated and focused at that point.
Right. So actually, it goes around the sun, and then so you can see beyond the sun because it's all going around. Right.
Yes.
Okay. I sort of understand that. Thanks
Yeah.
for that. So, have they found us?
Well, if we take the estimates from our book, and there's maybe a couple civilizations in the Milky Way, they're stupendously far away, so they might have a hard time detecting us. Unless they are much longer lived than we estimated. And this is perhaps the existential point that I like to leave people with. When we estimated the number of civilizations as like basically a handful in the Milky Way at most, this is with that doomsday argument that suggests that our advanced communicative civilization has a lifespan of a few centuries, which makes it sound like we don't have that much of a future. But if we were able to detect a civilization, the only way that that would be probable is if that number of civilizations is large. So that way they're close enough for us to actually detect them with our technology. And if they're close, that means it have to be plentiful. And from the Drake equation, there's only one variable that you can really crank up and get n to be very large, and that's the lifespan. Discovering that the aliens exist would mean they'd have to be long-lived, and again, from the Copernican principle, if they're long-lived, we're going to be average. We're going to be average like them. If they're long-lived, we're long-lived.
So, actually, detecting alien life is hopeful for us, and
Yeah.
that which is a really interesting ramification. Now, where we're going to go? So, this will be the last area we're going to talk about in this video. So, this is the first of a series, but actually, there's probably quite a bit to talk about here, which is, right, have they already found us? But surely they have. I mean, I've seen loads of ancient aliens shows. I've seen loads of UFO shows, and we're hearing in the news, like some guy recently has been talking about how there's been loads of sightings of aliens. So surely we've seen loads of aliens, right? I mean, they're out there. I mean, before you answer that or deal with that situation, I will have to say this, and that is, and again, it goes back to you using all of that energy, time, effort to go across a galaxy, maybe between galaxies, right? If you're going to do all this stuff, you've got an immense amount of technology, far outstrips our technology, which means that you should be able to look from afar and get all the information you need from a given planet. But if some of these accounts are to be believed, aliens have come all across galaxies, maybe between galaxies, all across this galaxy, and set up shop just outside of our ken, and then abducted some drunken dude and shoved the probe up his ass just to see what's going on up there, because of course that's what they want to know. They've come all that way to probe some guy's rectum. So and of course that's ridiculous, and so I would just out of hand dismiss those kind of accounts of alien abduction just because they make no sense to me. So just, yeah, load of rubbish. But what do you think are the very best claims of interaction with the intelligent alien life, and do you think there's any case for those to be true?
So I first try to think about, okay, if aliens were visiting us, who would have the best chance of detecting them? And the question is, well, who's looking up the most? Astronomers. And all of the claims, just about all of the claims of detecting UFOs come from non-astronomers. So how is it that the aliens are very good at hiding themselves from the best observers, but keep getting caught, and I'm putting these in quote marks, by those who are just haphazardly barely catching them, or having, in the more humorous case, having a drunk bender in the woods and waking up wondering what happened to them last night. And people might be pointing to, well, what about those videos from the Navy that were released? And it's like, well, first off, again, all of those examples are stuff that's like on the edge of like what the sensors are like barely picking up. And it's what Mick West has been calling in the LIZ, the low information zone. It's fuzzy, it's hard to tell what it is, and that seems to be where aliens and Bigfoot and things like that always exist. Because if they were in the high information zone, you'd be able to tell, it's like, oh, that's not Bigfoot, that's Uncle Phil. No, that's not an alien spacecraft, that's a Boeing 747, etc. They're always on that edge of like, there's barely anything you can tell, and your imagination is kind of filling in with the more fantastical. And when one is a little bit more careful and critical, you can come up with much more down to earth explanations, even for the alleged UFO videos that have been released from several years ago. And again, I name drop Mick West. He's probably done the most in either himself doing the research or gathering together other people who've made observations to point out, oh, we can explain this as only the appearance of rotation because of the sensor on the aircraft that was seeing this thing in infrared, for example. Or this thing that looked like it was going super fast, if you just do the basic geometry from what the sensors were reading, you realize, oh, it's only moving at 40 miles per hour. It's probably just a balloon. Things like that. So those best examples don't turn out to be great. And of course, if you're going to be saying, well, what about the most recent whistleblower? I would also like to point out to you, everything he said had to be allowed by the CIA to not be classified. So if he's saying there is a secret alien program and the CIA basically says, yeah, that him saying that is not classified, that basically tells you there's not a secret program because it would have been classified at the very least.
Absolutely, yeah, yeah. So is that to say that you are fairly dismissive of these claims then?
I don't like to say dismissive because it makes it sound like I'm intransigent, but I do look at the history that this same kind of thing of somebody coming out and saying they're a whistleblower, they have some new info or whatever that shows alien tech has been going on for decades. And every single time, nobody comes home and brings home the bacon. And there's only so many times you can hear that and not become pessimistic that someone has good information.
I think it's just a case of wishful thinking with a lot of people because it's just something that people desperately want to be true. It's exciting, it's cool, it's conspiratorial. All of these psychological sort of characteristics, I guess, mean that, yeah, there's going to be a lot of people really arguing that this stuff happens. But the stark reality is that there's a exceptionally low probability, just scientifically, circumstantially, from a kind of just doing a Bayesian analysis kind of competing hypotheses. What's the most likely? Aliens is actually it's the most exciting, but it's the least likely explanation of the data.
Exactly. Yeah. When we say, hey, at best or at least our best estimates would suggest there's a few civilizations in the whole Milky Way, which means it's hella hard for them to get here. So there's already a low probability that they are out there and close enough to make the trip worth their while. And then on top of that, the evidence that the astronomers never seem to pick them up. And then the only sort of evidence that exists there is of the lowest quality out there. And it's like, okay, we need better. And in fact, in some ways, the most pro-alien scientists out there have accidentally, I think, undermined the UFO videos in the following way. So one of the astronomers who has probably been the most gung-ho for saying we detected an alien probe was Avi Loeb from Harvard.
Right.
He was saying that like this object known as Oumuamua was actually some sort of alien tech light sail. I show reasons in the book why that's probably not the case, but one of the things that he did in a paper that was published with one of the administrators for this group that's been doing all this research on UAPs, or unidentified aerial phenomena, being recorded by the military. They basically came up with this paper saying, well, if the aliens were coming here, they probably would have come by mothership and then a whole bunch of other smaller ships to do the things. It's like, okay, that's, interesting, but science fiction-y, but okay. But in that paper as well, they also basically say, well, if these vessels are going through the atmosphere and they're moving at the speeds that the pilots are saying they're seeing, if they're saying, hey, that thing just, turned 90 degrees going Mach 20, we realize, well, that is going to leave a noticeable effect in forms of basic physics. If something's going that fast through the atmosphere, it's going to make a sonic boom. And something going through the atmosphere that fast is also going to compress the air and make it like super hot, and even at a plasma, which basically means you're going to see this hot trail as it goes through the atmosphere, no matter what kind of propulsion the aliens have, because they're simply moving through the air and compressing the air, like that. So just basic physics would suggest they would leave a very noticeable trail of heat and sound that the observations never seem to pick up. So accidentally, Loeb's scientific analysis there undermines the people saying these Navy videos are showing fast alien vessels.
So yeah, because I was going to ask you about this Oumuamua, if that's the correct pronunciation of that. So it's now deemed a comet rather than being a big alien spacecraft.
Yeah.
What about ancient aliens? Because everyone loves an ancient alien, right? I mean, they exist. Yeah.
Well, there might be ancient aliens, but that doesn't mean there are any ancient aliens here on Earth. I think more likely than not, if there has been life in the universe, some of them have existed for a long time, but also may have also gone extinct. Has anyone come here and decide, you know what? I like this planet. You know what this needs? Giant pile of rocks. Okay. Because with the claims that the aliens either built or helped in the construction of the pyramids of Egypt, for example, are not well grounded. Now, be cool if true, but the thing is, we can actually tell how the ancient Egyptians did it and can actually basically see their centuries of progress in developing their pyramid making techniques. It was not just like one day they're just, banging rocks together like cavemen, and then the next day there's a giant pyramid. It's more like, no, this is a few centuries of development in burial practices, construction projects, and mistakes. Because we see the mistakes left over as well.
Yeah.
Best case scenario, if we're going to actually find ET from the past, evidence of that, is the same way we see other cultural interactions and see what happens when two very different cultures come into contact and what sorts of artifacts they leave behind. And I give some examples of that in the book. So, for example, when people from Europe came over to the Americas, you can see that in the archaeological layers, that you can look and see, okay, here are Native American artifacts of various forms, and all of a sudden you're here in New England and you see this nice china, and you're like, okay, this is not what the native population had been producing, but this is the sort of thing that folks in England were producing, as an example.
It's the same kind of theory about finding a rabbit skull in a Precambrian rock strata, right?
Exactly.
Like that would disprove evolution, and it hasn't happened. And at the same time, we haven't found the evidence where we'd expect to, like the argument from silence being relevant here, and being being a decent argument to use, and it works, the argument from silence, if you expect there to be evidence, and there isn't evidence, then that is disconfirming evidence of that being
Yeah.
a true claim. So if you had ancient aliens and there's just absolutely no evidence of them being there where we'd expect there to be evidence, and that is itself disconfirming evidence.
Yeah. And the key thing is evidence that we would have expected to see. It's from, I forget which Sherlock Holmes detective story. It's the dog who didn't bark. In this sort of case, it would be if aliens did come and gave advanced technology to such and such group, we would have seen this amazing discontinuity between what was there before and what came after. But we see continuity instead. So we don't hear the dog barking. We don't see the discontinuity that this advanced culture coming in would have produced.
And I think this is where you can also talk about motivated reasoning, which is that, there's people making a lot of money off this. There is TV channels, Ancient Aliens and a History Channel, and there are books and there are magazines and websites. People make serious money out of this, and there is a really good indication of why those theories might prevail and why there are people who supposedly believe them. Or there are people who genuinely believe them, but they're sucked in by this whole, sector of money-making enterprise.
Yeah.
I would.
And it is worth noting that on the History Channel, they will give you sensationalist stuff and pretty much come right up to the line, and maybe even across the line, of lying to their audience about things. So let me give two examples of stuff that the History Channel has done and try to see what they could get away with. So when we were on Gnostic Informant a few weeks ago, I was talking about this program called Hunting Hitler, which was this conspiracy theory that Hitler didn't actually commit suicide in the bunker in Berlin in 1945, but actually escaped and eventually escaped to South America. In that show, they claimed to have actually found a picture of an elderly Adolf Hitler living in South America, and said they did this facial recognition stuff on it to confirm this definitely was Hitler. But the reality was that wasn't a picture of an elderly Adolf Hitler, but of a older Mo Howard of Mo of the Three Stooges. And the thing is, they figured out before like the episodes aired that this actually was Mo frickin' Howard, who was Jewish, by the way, now being called Hitler. They realized, this is kind of
Brilliant. Brilliant.
So they started actually like blurring out the image a little bit when they were transmitting it. So they weren't even showing like the picture proper because they realized, this is like real cringe calling a Jew Hitler. So let's kind of muddy the waters there. But if you look at like the older trailers where it's clear the image and you realize, oh, they went back, they doctored it so that way you can't tell, oh, it's Mo frickin' Howard. So yeah, that is them knowing. Yeah, this is them knowing they fucked up and they went with it anyways because they already had the time slot. They're going to make the money either way. More recent example, more alien related. One of the shows on there is called Secrets of Skinwalker Ranch. I think that's the title. Skinwalker Ranch is this place where is claimed all sorts of paranormal activity, whether it's ghosts or werewolves or UFOs, what have you. All the sorts of stuff is claimed there. And the group there said, hey, in our video, we just saw a UFO fly by, and we just estimated that it was going 3,000 miles per hour. In the trailer video, and you look at it carefully, you can actually see this object that's moving along is flapping little wings. It's a bug. But in the actual transmitted episode, they've gone back, it looks like, and now made it so you can't tell there were actually wings flapping. Which to me is, if not lying, it is close enough to basically say it is not trustworthy television.
Yeah. So I think we can safely dismiss Ancient Aliens and certainly the History Channel. So what we've done, hopefully, is given people a kind of a basic grounding in ideas of aliens, chances of aliens existing, so on and so forth. And what we do, the kind of TLDR of this video would be aliens exist out there. There will be intelligent alien life forms existing out there, potentially billions and trillions of it, of examples of it. I mean, talk just a little bit before we end this, talk a little bit about the observable universe. The idea that actually the universe is insanely big at our best estimates, and some would say infinite. It could be infinite. So talk to us a little bit about the size of the observable universe.
Yeah, and that key word there is worth highlighting, observable universe, because we need to specify how far can we see, because the speed of light is finite. And so if something is further away than there is enough time for its light to reach us, we can't possibly see it. And it's a little bit more complicated by also the fact that in the early universe, it was expanding at this accelerated rate. So our observable universe is many tens of billions of light years. And again, to give this sense of scale, a light year is the distance that light travels in one Earth year. Our nearest star to our solar system, Proxima Centauri, is 4 light years away. To cross the Milky Way, that's approximately 100,000 light years. To go from the Milky Way to the nearest major galaxy, the Andromeda Galaxy, that's about 2.5 million, with an M, million light years away. The most distant galaxies that we can detect are on the order of 10 billion light years away. So more than 1,000 times further away than the Andromeda Galaxy is away from us. And then that's just getting to the outer edge of what is observable.
Is that all spherical? As in, like, can you look in all directions? Or is there like a flat, a diskness to existence? Or is that just one galaxy exists in a disk, but actually you can still look? There are then lots of galaxies in all directions that you would look.
The main thing, or the major conclusion in cosmology, is that the universe is mostly isotropic. It's pretty much the same in all directions. So look left, right, up, down. It's the same general density of galaxies in all directions.
So in other words, we are looking from here, and we can see to a maximum of how many light years?
I forget what the cosmic limit is, something like 96 billion, but I could be getting my numbers mixed up. But on the order of tens of billions of light years, which is a big number, but it's well short of infinity. So the question is, what's beyond that limit?
Yeah, because
And
that's just an arbitrary. That's a kind of like an arbitrary stopping point. And of
yeah,
course, the question is, we don't know how much further beyond there existence, stuff matter is goes
yeah,
on for.
yeah. We have every reason to know that there is stuff beyond there, but how far beyond? And right now, our cosmology is consistent with a universe of infinite spatial dimension, that it could go on forever and ever and ever.
So the end result being that there is almost certainly trillions of life forms out, intelligent alien life forms out there. This would be my conclusion. I'm not speaking for you, Aaron, but I would say there's almost certainly trillions of intelligent alien life forms out there, but potentially infinite numbers
Yes.
thereof, but just huge numbers, just separated by. I mean, we're talking about trillions of galaxies that we know about that are
Mm-hmm.
separated. That you arguably aren't going to be able to go between, so on and so forth. Or
Yeah,
if you
and of
do,
course,
then
we're still even just talking about one universe. We're not even getting into multiverse hypotheses, which would further multiply these numbers.
so that's our conclusion now. And then where we're going to take this is right. Given the plethora of intelligent alien life forms existing out there, what does this say about our place in the universe, and what does this say theologically, philosophically, theologically, particularly looking at different religions and particularly looking actually at Christianity? So, is this what we would expect? Given the revelation that supposedly is the Bible, does this situation, does this reality of trillions of intelligent alien life forms existing, does that lower the probability of omnigod existing, the Christian omnigod, for example? And we will do a part of the video on other religions, but we'll focus primarily on Christianity. And does this really affect the probability of that God existing? And we'll hopefully show you that this has a negative effect on the probability of God, of a Christian omni-God existing. But we'll get to that in the next episode. In fact, the next episode will start with doing a bit of psychology. How would we react to knowing or discovering the existence of intelligent alien life? How would we, as secular, non-religious people, react, like you and I? How would religious people react from a psychological point of view rather than a kind of philosophical, theological point of view? And then we look at the interaction between such a discovery and theology, and the implications thereof. So, does that, hopefully that makes sense to the viewers? Is there anything else that you would like to say in terms of what we've discussed already, and where we're going?
I also want to note one other thing that's worth bringing up when it comes to the search for extraterrestrials, that there are scientific ways of doing that, of trying to detect that technology, but we also have one other way of refining our estimates of life out there, and that's continuing to explore our own solar system, because it could be the case that in the past there was life on Mars. We still don't know for sure, and there could be life in our solar system on the moons around Jupiter and Saturn, around Europa and Enceladus, that those are places that we know have liquid water under their surfaces. The question is there anything else swimming in those oceans? Answering those questions will go a long ways to helping answer the question of, are we alone in the universe, by finding out, are we even necessarily alone in the solar system? And that is in
Still an
our
open question.
near-term future scientific endeavors. We might know within my lifetime if we have fishy friends in the waters of Europa.
Yeah. If there's any questions anyone has for the topics we discussed tonight, this kind of more science heavy, cosmological heavy, astronomically heavy, that's really heavy. You know, stuff that we talked about, you get them in now. SK says here, actually, we should calculate an approximate, and I don't know if you can make sense of this. Actually, we should calculate an approximate assumed size of the universe now. I mean, we calculate Big Bang to milliseconds. So, how, I guess the question would be, how do you get an infinite sized universe from arguably is there a finite amount of matter densely compacted at the Big Bang, or is there infinite? Can you have infinite matter? Play around with these ideas.
Yeah, so the thing is, you don't actually need so much infinite matter, is that you basically need this balancing act between the amount of energy that goes into a universe and the form of negative energy that we call gravitational potential energy. And that balancing out would actually mean that the universe would have infinite size. So ultimately, from general relativity, we can do something to measure the geometry of space time itself. And if it is the case that it is perfectly flat, that means it would have infinite extent. And this is also a way of saying what is the density of all that matter and energy throughout the universe. If it's close to something called the critical density, then we have basically this perfect balance and that the universe has infinite extent. If the density is a little bit too high,
by extent, do you have infinite amounts of stuff? I mean, in order to have distance, you've got to be able to measure that in terms of stuff, right? So
yeah.
that would assume there would be infinite matter.
Yes, that would be true. It would always be nicely balanced out by an equal amount of negative energy in the forms of gravitational potential energy. So that way, for every dollar you take out of the bank, some other source of money has gone back in to keep the ultimate balance to be zero.
I guess like there's potentially no problem, although we get into mathematical infinities and whether you can have an infinite set of stuff. But the question from me as a layperson who knows not these things and asking our in-house expert here, how can you have infinite matter packed into like a finite space? Or do you know what I mean? Like,
Yeah.
it depends on the interpretations of the Big Bang and so on.
Um, so that's why I keep also highlighting this balance between the positive energy in the form of matter and the negative energy in the form of gravity. That if the two are always balanced at zero, if you're taking a positive and negative and they always add up to zero, then you can start from zero and have an infinite amount of stuff, but just always balance that out.
So that's kind of Lawrence Krauss. How do you get something from nothing book that I've got
Yeah,
back there, talking about that net zero basically.
exactly.
Yeah, yeah.
Yeah, and like I say, the thing that would actually allow us to tell what that is we're measuring what's called the critical density, and our universe seems to be at right about that value. But to know exactly what that value is would require infinite precision, which you just can't get with astronomical instruments or scientific instruments generally. So we seem to be like a universe that looks extremely close to flat, but we can't tell you that it's perfectly flat because it requires infinite precision. So the universe is at least consistent with having infinite size, but we cannot confirm that because it requires measurements that can't possibly be done.
That's a really great, concise conclusion there. I mean, my conclusion, my interpretation of that, and thank you for that, Aaron, is that the universe is at least really bloody big, and I think that's probably where we should leave that. If there are no more questions from anyone else, thank you for those who have been commenting in the live chat. We'll look to hit you guys up with the second part to this, maybe next week, same sort of time. I don't know what Aaron's schedule is, but at some time soon. And I imagine, we'll look to do. I think we could. This series will probably go on for about maybe 3 videos worth. I don't know. We obviously don't want to tell you everything we talk about in this quite marvelous book that you should all buy 58 copies of. But we will be going into good amount of detail. I love this. Could listen to Aaron infinitely. I love how me, on the other hand, is like, not so much. He's a bit sucky, but Aaron definitely he can talk and and I love listening to him. Yes, so thank you for that. This is the book. Please support our endeavor here by grabbing a copy. You don't have to read it, of course, but just just tell us the last thing to say before we leave you guys. It will be about the cover. So tell us, talking, because I know that in the chat, Kathy was talking a lot about AI, and I think Paul as well was talking about AI. So tell us about the cover here.
All right, so I don't know about you guys, but I am still working on the stick figure. I have no great artistic abilities. So I wanted to see, okay, all this stuff was, starting to get big last year about artificially generated art, artificially generated by artificial intelligence. So I put a few different text prompts into DALL-E, specifically DALL-E 2, and try to see what sorts of things could it produce. When I said, well, what about science and religion, or aliens and religion, science and the stars, things like that, and it produced this central cover image of this moon beaming down Revelation into this book with the burning Moses bush down there, and it was just yeah, the computer got it. The computer knows what I want. So we used generative AI to produce this image. We use much less generative AI to produce the inside of the book. That's mostly the more squishy forms of intelligence that we've been used to.
Absolutely. Basically, we hate graphic designers, and we want them to all lose their jobs. So we went to not true. But yeah, I thought that was a pretty interesting cover. Fantastic. Thank you, Aaron. I really appreciate that. And by the way, if anyone has read this, we've only got one. It's relatively newly out, but it's only got one review so far. So if you like the book, please review it favorably. We need to get onto that and make sure people who have it are reviewing it. And thank you, SK. So thank you, Jonathan and Aaron, for the great evening and multiple ideas around life, science, universe, and cosmology. I love that kind of variety. So pleased that you have joined us here. I've enjoyed this tremendously. Thank you, gentlemen. Thank you, series. Really appreciate you being here. In the meantime, thanks so much to Aaron. Thank you to you guys for watching. We'll be in touch soon. Aaron, I'm going to give you the privilege, I hope, of having the final words.
I like to think back on our search for aliens and remembering the last lines from the classic movie, The Thing from Another World, where the movie ends with a call to the rest of humanity to keep looking to the stars.
Absolutely, and I said you were going to have the last words. I'm not going to take the last words, but there was a quote. Is it the end of the book? I will save that for later. But thank you anyway. I won't go on. Thank you, everyone. Thanks, Aaron. Take care. See you all later.
Bye bye.